back again. It means that day one was great. So you're back again for more sharing and learning. And I learned a lot yesterday. I believe many of you did as well. And so we look forward to one more day of learning as well. I would like to acknowledge the traditional owners of the lands on which we meet on today, the Yagra and the Turrbal people. We pay our respects to the elders past, present, and emerging. We also want to acknowledge the team, especially the Kana, Shunyao, Wendu, working behind the scenes to make everything work. Running a hybrid event is not easy. So yeah, let's acknowledge them, and also Grant as well, helping us with the industry relations part, making sure that it's known to our industry partners. So a lot of work goes behind the scenes. Just pat them on the shoulder when you see them at a tea break, appreciate them. So today we have a few sessions. The first session will be chaired by Associate Professor Mark Arting. May I invite Mark to come to the front to start his chairing? Thank you.
Oh, I don't really need a clap. I'm not speaking yet. Welcome, everyone. Yes, our first talk is going to be online, and just going down to the full schedule. The session is on AI security and security for AI, which is a really important topic. And there are some conferences starting up on this area now. And our first speaker will be Mr. Kuhn Han. Are they online? Yep, good.
Yes.
You ready?
Yes, thank you.
Excellent. I'm speaking on temporal analysis for cyber attacks detection. So we have 20 minutes. So 15 minutes talk and then 5 minutes questions. Thank you very much, Kuhn.
Okay, cool. Thank you for your introduction. I'm going to share my screen. Can you see my screen now?
Oh, yes.
Yes, cool.
Just a moment. Yeah, that's right. Yeah, good. Thanks.
Okay. Good morning, everyone. My name is Kuhn, and I'm happy to be here to share our current research, which is temporal analysis-based machine learning techniques for cyber attack detection. Before talking about today's research, I'm gonna share some background about our project. We're focused on the time series data, which refers to data collected over time with each time point and will be associated with a time step. This kind of data is very common in cybersecurity, such as network traffic, user behaviors, and system logs. Cyber attacks often follow some specific temporal patterns, such as the specific time of the day or how long it lasting during the whole process. And from this figure, we can see the attack derail time has increased in the past few days. For example, some of the attacks may remain on the system more than 4 and 28 days, or some of them may stay in the system more than 1 month. So focus on the temporal patterns of the attack behaviors is very essential for cyber attack detection. And by analyzing temporal patterns will give us and help us to do the detecting and preventing the cyber attacks in the early detection behavior. And here is the example of the temporal analysis for cyber physical system. We can collect a lot of data from the different components of this physical system, including the power system, the treated water system, and also the manufactured gas system, and also a lot of information from the interactive system like the network flows or the software logs. And after the collecting this kind of data, we can do the monitoring and analysis, and also the remote control if there is a potential hacker behavior happen. Based on this, we can see analyzing this data in real time is very important because we can give a real-time process and the real-time response. And also we can have the real-time analysis for the data to give a late detection of the threats. The prevention techniques can be machine learning based or AI based, and which benefits the cybersecurity a lot. For example, we can see AI learns more over time, and AI identifies unknown threats, and also AI is capable to handle a lot of data and also the reduce duplicate processes. In short, we can summarize the three main points, which is automation, which reduce the manual work, and adaptivity, which adapt and learn over time as data coming, and also scalability, which means the AI-based methods can analyze large complex data and multi-source data. However, the machine learning methods have some weakness as well. The first thing we're going to talk about is the data format requirements, which means the machine learning models always require the well-aligned fixed lengths and no missing data during the training process. But this requirement is not real for the cybersecurity scenario because the data we collected will also suffer from the missing due to the device's failure, network lagging, or the software error. For example, if you look at the collected data, they will have a lot of zero values in them, but we cannot simply assert that this zero value means nothing here or nothing coming. We don't know the zero is due to missing or just no values coming. So handle this kind of irregular or missing data is inevitable in our real life. And another weakness is about the human annotation requirement, which is the labeling in the machine learning methods. In real life scenarios, classify the multivariate time series can be very challenging due to the lower interpretability of the real value sequences. As a result, posting this kind of data will be more costly concerned with the class data such as images or text. So the labeling is very expensive for this kind of questions, and this presents a significant constraint for multivariate time series classification problem. And also interpretability is another issue of the machine learning methods. Machine learning based methods are always limited interpretability, which means they are difficult to understand for security teams. For example, for a real-time monitor system, the machine learning methods or the model will alert the user by analyzing the multi-source of data. However, the security may want to double check with the model why it gives us alert, or how can I check which process comes error like that. But there's no interpretable way to make the security teams understand how the machine learning model works. Based on this weakness, we propose our overall objectives of the research. We're going to develop efficient and reliable real-time learning techniques for cyber attack detection with limited resources. The keyword here is correlated to the before mentioned three weaknesses. And we, for easy understanding, we separated to the three sub-research questions. The first one is handle data format irregularities and provide efficient detection of cyber attacks. The second one will be the handle low quality human involvement and provide robust detection of cyber attacks. And the third one will be handle non-interpretable output and provide understandable detection of cyber attacks. This remaining research question will be the different part of the problem solving, and it will follow the logic like this. By doing this, the final solution to this problem will make the user have a reliable machine learning solutions and also a easy understanding decision-making process. And today I will focus on the first research question. Here is some previous research methods to solve these problems and also the limitations of their methods. As we all know, a lot of different neural network has been utilized in this area, in this field, and also they have achieved a very good performance, but they do have some limitations to need to be solved. For example, the graph neural network based methods, they will rely on the studied graph structure and also they rely on the prior knowledge about the graph structure, which means they have to know something before you get the data. This is not, this is a very hard for the real application during the in our real life. And also for some transformer-based methods, they will have the big research gap, like the utilization of the future information. Because of their model structure, they have to get access to the full data. But this is not suitable for the streaming data because when we get the data in streaming way, we cannot get access to the future information. And also, this kind of model cannot give the real-time prediction or the real-time analysis. Motivated by this, we propose our solution to it. We're going to using graph neural network to deal with the data irregularities, but we don't have to access to the prior knowledge of the graph structure before we training the model. What we're going to do is we are using the current available data and approximate the graph structure during the training process, and then we make the graph structure dynamically changing with the new coming data. And by doing this, we will have a dynamically graph representation about the original multivariate time series data, and then we use this data to represent the temporal patterns of the original correct data. Here is the problem formulation about our research problem, and we need to note that we focus on the irregular multivariate time series data, and also we're going to learn a sequence of temporal dynamic graph, which means for each time point we're going to learn the graph for the current irregular multivariate time series data, and also we will going to learn a final unique graph representation for the irregular multivariate time series data. And here is the overview about our proposed framework. It includes two parts, spatial temporal encoder and temporal spatial decoder. The first step, or the left side of the model, will be the we'll learn the lower dimensional representation of the original data, and then we're going to use several simple classifier to do the classification to see whether this kind of data means there is a attack happen or not. And also we can use the right side part to recover the original irregular multivariate data to impute the missing values. By doing this, we can solve the different downstream tasks like the classification and imputation. The core part of the model is the dynamic structured learning strategy. It includes two parts. The first one is the local information approximation. We're going to analyze the dependency among the sensors or among the nodes in the graph. And for each time point, we're going to learn a graph for the current time series data. And then we utilize the learned graph structure to share the information from the different sensors or different nodes. The missing sensors on the nodes will get the information from the observed nodes. And then in this way, the missing impact will be reduced. And as long as the training process, the graph structure will be more reliable and the information share will be more reliable as well. And to counter the irregularities, we also provide the intersample information share strategy, which utilizes the attention mechanism to get the global information. By doing this, we can reduce the data irregularities and the noise impact and make sure the learned graph is reliable enough.
Kun, 2 or 3 more minutes, so we've got some time for questions. Thanks.
Yeah. Okay, and so I will give a quick look about the experiment results. We can see the for the imputation task, we have a very good performance. And for the classification, we can also get a better performance compared to the current state-of-the-art methods. And what we want to point out is that our graph can evolve with time during the training, and also our graph will converge in the end, which state that our strategy works in the experiment results. And another interesting find is that the graph structure is all the same as the calculated by the numerical ones. Like, for example, the graph here is calculated by the Pearson coefficient, and here is the graph we learned. The dark color means the sensors are correlated or the sensors are highly dependent. We can see these two graphs is not same, which means the numerical information is not always beneficial for the model training. And also some of the nodes may have very highly importance during the model training, which means which gives our insight for the real application. For example, monitor some center nodes in the whole system will give us more reliable insight about the current state of the system. And here is the properties of our proposed methods. We can see our model can model the irregularities without imputation or prior knowledge. And also we can learn and approximate a reliable graph on the stream data. And also we can provide real-time and early detection. For the future work, we are going to handle the following research questions, like the handle low-quality human involvement and provide a robust detection of cyber attacks. We're going to try some active learning strategy or semi-supervised learning strategy to make sure the lower requirement about the labeling efforts for the proposed methods. And that's it. Thank you for your listening.
Thank you. Thank you, Kun. Do we have any questions? I'll start off with one. So if I understand you correctly, it looks like there are potentially a stream of events coming in, potentially hundreds or thousands of events per second. And as each one comes in, you're updating the graph. Do you run the machine learning every time the graph is updated, or do you only run it, say, every second or something?
It depends on how you handle the data. You can make some pre-processing of the data. You can construct the data into a different format. For example, you can define the time frequency you construct the graph. So, for example, for our own experiments results, the data may collect in every single seconds, and we can combine the data to every minute or every hour, something like that, to make sure the process will be quicker or
yes, I see.
Yes. It depends on your demand, depends on your applications.
Yep.
Yeah.
I was just wondering about the human interface of it. If there are potential machine learning results, many times per second, that might overwhelm the user, but you can slow it down.
Yes.
Yeah, good. Thanks. We have another question.
Hello, Kun Dan. I have one question about what type of attacks you are going to detect using the zero time series analysis.
This is a very good question. The current research we focus on the general cyber physical system attacks, and the current proposed methods will solve the general multivariate time series classification problem. So we don't focus on the specific cyber attacks now, but we are trying to do now is to collect and construct the specific cyber domain problem and cyber security related data set, and then test the performance on it. We are still trying to do this now. So that's it. Answers the question.
Can I ask
Yes,
a question?
Thank you. We have a question online as well. Would you like to ask your question, please?
Yeah, sure.
Yes.
So I would imagine this data set is imbalanced data. You didn't talk about that, and probably also intermittent data. So how do you manage that?
Thank you for your question. The current model doesn't focus on the handling imbalance. Now, for the imbalance data set, we are simply use the oversampling and undersampling to make sure the training data set is balanced. So we don't propose some specific techniques to handle the imbalance for our methods.
But if you look at your history of your time series, say you have got 10,000 observations, because it's a high frequency data, I would imagine. So from these number of observations, you only have probably handful number of attacks, or let's say hundreds of attacks.
Yeah.
And if you want to train your multi-label classification model based on, say, thousands of observations, and where you have only a handful number of labeled data that they're attacked, basically, I mean, the model wouldn't learn them properly. So I'm a little bit confused on that because the models that you have, the performance that you showed, and you benchmarked it against a few other methods, didn't have all the information about the F1 score and how you do on the accuracy and things like that. But that's fine. No worries. I would also just suggest you to compare it with a very simple benchmarking method, not graph neural network, but benchmark it with logistics regression and see how you perform in comparison to a logistic regression. And a great work.
Yeah, thank you. Thanks for your suggestion.
Yep. I think you might like to discuss that further offline. Let's thank Koen again.
Thank you.
And move to our next speaker, Subrat Swain. Speaking on adversarial machine learning. Thank you very much. I'll let you know when you've got 2 or 3 minutes left. I'm telling you there's 2 or 3 minutes left of your talk.
The pointer, you want pointer? This one. So this is the point you can change the lights.
Hello. Yeah. Good morning, everyone. So this is Subrat, and I am here to present our joint work with me and like my prof at IIT Delhi and here at UQ. The work is SPART, semantic preserving adversarial transformation for generating perceptually similar adversarial examples. In recent days, we have seen that AI has been everywhere. Like we can see drones and self-driving cars and voice assistants, and we can see using AI in our everyday life. But the problem with AI is that this is a basic model. So this is called a DNN, and the way it operates is that it takes a input as a input image as input, and at the end it gives like this sort of probability scores to the different classes. So here you can see that it has given 0.9 probability of this image being panda, and a very low probability for other classes, let's say gibbon. Recently it has been not recently, like it's been a while, it has been found that these ML models are not safe against adversaries. So what is the thing is that these adversaries can add a tiny bit of perturbation, which will not make any difference in the original image, but as a result the confidence level of the classifier for a particular class will change. Like here you can see that the confidence level for of classifier has changed from panda to gibbon. So like in diagram you can see that like here's a panda image, and it is an adversarial example, and it has noise in it, but it is not visible. If we pass this panda to the neural network, the confidence level of panda has dropped and the confidence level of gibbon has improved. It's like 85% gibbon and 24% panda. To formalize, I'll just give a taxonomy of what these adversarial attacks are. So we have an original image that we called X, the panda image. We have a adversarial perturbation or adversarial noise, which we call delta. And we have the resultant adversarial image, which is called adversarial image, and we named it as X adversarial. If we just superimpose these two images, we'll get the adversarial image. And this is our model under attack. We named it as F. So a basic adversarial attack formulation is formulated like this. So what do we need? So the research question, the question people generally solve is that how to get this delta, how to get this noise. So the noise should be such that the perturbation should be such that number one, it should evade the model under attack, like the confidence level of the model should drop. And number two, the resultant adversarial image should resemble with the original sample X, the original image. Because if the model is classifying a panda as a cat, and it is looking like a cat, then there is no point, because we also know that it is looking like a cat. But if the panda is looking like a panda to a human, but the model which is a state of the art, which is have a accuracy of say 98%, is saying that it is a cat, then that is a problem. So here is a little optimization problem that is there. So you can see that. So I have put the term evade in red, and this term in the optimization function as red, which is like evading the system. So to evade a machine learning model, we have to maximize the loss. So you just have to remember that the lower the loss, better the model is, and to make it fail, we have to increase the loss. And there's a second term, resemblance, and there's the second equation, the delta, the L infinity norm of the delta should be less than equals to this epsilon. We are looking for more resemblance. So you can say resemblance means the distance between the original and the final should be less than some epsilon. It should be bounded by some epsilon. So these are the two goals people generally look for when they create an adversarial example. It should evade the system and it should resemble with the original sample X. So keeping this goal in mind, different adversarial machine learning algorithms have been proposed in past years. And so we called in our work these as conventional adversarial machine learning attacks. And we saw that like these attacks directly add noise to the input image. Suppose this is an image of 8, we add noise directly in the 8, we got a perturbed 8, and it is predicted as 3. And we measure this noise as a LP distance. So LP distance is like a Euclidean distance, but in term, if the P is 2, it is Euclidean. If the P is infinity, it is something else. So you can just change the value of P and get different norms out of the noise. And we measure this noise using this the LP distance between 2 images. So the limitation that we found in all this conventional AML attack is that as they are directly adding noise in the image directly, so it can hamper the semantic of the input. So we can see that in some cases the noise amount has to be very large to evade the system. And as with the increase in attacks, we have also got also more and more defenses which can detect all these things. So why do we care about semantics? Because like some images like face images or some images where we want to hide the perturbation like very cleverly, we want the semantics to be preserved. So with this goal, we wanted to generate semantic adversarial noise instead of the normal adversarial noise. So the attack formulation, we changed a little bit. So the first goal remains the same. It should evade the model under attack, the F. But in the second formulation, instead of we're like looking for resemblance, we look for the original and the attack sample should be perceptually similar, not just similar. So the change to the optimization function is like the above, the red one remains the same, but instead of the Euclidean distance, we are looking into now a similarity metric that can find the similarity between the input sample and the adversarial sample. So, how do we measure this similarity? Like there's this S, I put just S, but how do we measure this similarity? And how do we measure a human perception? So because, for example, like if I take an image of a cat and I shift all those pixels to right by just 1 pixel, it will still be a cat, but there will be a lot of difference between these two images if you just take element-wise difference between those 2 images. So what I wanted to do is that we wanted to capture the human perception, not just the element-wise distance between the two images. So we in work we found that the internal layers of a neural network is closely approximates the human perception. So instead of directly taking difference between 2 images, if we pass those 2 images to same neural network, and we get a representation of the neural of those images, and we take a difference of that, it will be similar to human perception, and it will be like will be a close approximation of human perception, and we call this as the LPI page distance. So we had our like the first argument, which is resembling with the first goal. So we have had that. Now we have the semantic distance, which is the internal representation of a neural network. So we have both of the things that is required to solve this equation. And we sort of proposed a framework, which is a unified framework, which sort of took all the existing adversarial attack algorithm, and then it converted it to its semantic version, such that the resultant image that we get will be more semantic, and the images will be perceptually similar to the original image. And the problem, so the problem that we solved is that we found a better way to hide those noises inside the images, such that it will be more difficult and it will be more stealthy for an attacker. So this is the thing that we did. What we did is that instead of finding the X adversarial, we trained the autoencoder. So what an autoencoder do is that it takes an image, it creates a hidden representation, and from that hidden representation, it reconstructs back the original image. So the profit of doing the profit that we get doing is that we get a hidden representation that is capable enough to get us the original image. So what we did is that in our method, we saw instead of finding the X adversarial, we found a Z adversarial, which is like a hidden representation of the true image. So since this internal representation capture the human perception, so the Z adversarial will be perceptually similar to our original image, and to get the original image back, we reconstruct our original image from this Z adversarial, and this is how we got our X adversarial by decoding it. And these are so these are some of the results. So you can see that the first row is the original image, and the second row that we generated using a conventional adversarial attack. So these are there's an attack called PGD, so projected gradient descent, and we use that, and we got these in these images in the second row. So you can see that it's a bit noisy, and the third row is the noise that we put to get these images, which I just took the difference. The fourth row is sparse PGD. So our method is sparse. So we just converted every attacks to sparse X. So X is any attack. So this is the sparse PGD, this fourth row, and the last row is the noise that we are putting in our attack. And you can see that the noise is almost zero, like it is very stealthy and it is very hidden inside the images. And so there are some quantitative results. And so we have put in the y-axis the attack success rate, and in the x-axis the LPAPS score. So attack success rate is that if a model is performing at its best, like say 100%, and so if a model is performing at its peak 100%, and if we drop the accuracy, then the attack success rate will be more. Like let's say the model accuracy was say 90%, and after we craft the adversarial attack, the accuracy dropped down to 10%. So the attack success rate will be 90%, because the accuracy is now 10%. It's just the opposite of the accuracy. So the more the attack success rate, it's better, and LPAP score, the less it is better. So from this graph, we can say that all those points which are in the left top corner of the graph are better. So we compared our results with SPART PGD, and SPART CNW. So all these are attacks basically, and this is for a data set that is called Cypher 10, which I showed in this slide. This is a Cypher 10 data set, and we also showed our results in a another data set that is called GTSRB. So GTSRB is a data set for road signs. So we also got better results in that data set as well. Yeah, so thank you for your attention. Any questions?
Very interesting results. What questions do we have?
Hey, how's it going? Oh, geez, what do I hold this? Here? Is here okay?
Yeah.
Okay, cool. So in the optimization problem that you had for generating the adversarial noise, you were using the L infinity norm, right? So to me, instinctively, it kind of makes sense how you can get these big local deformations of an image, because it's like most of the differences can be zero, but then in one little neighborhood, you can have big differences, and yes, you're still constrained fine. So you can turn like a 1 into a 7 or something like that. And so semantically, that's different. And did you benchmark against all of the other LP norms? Because like I feel like if you're using an L2 norm instead, you don't have that problem. It's like each pixel in each color channel is only allowed a little perturbation. Like, so what are these benchmarked against? Is it just the L infinity norm, or is it a whole other family of norms?
Yeah, so we did only in L infinity norm, I guess. But I mean, if we take a L2 norm and we convert it to the semantic version, it was coming, I mean, it's a better L2 norm. Like, I mean, in the L2 norm itself, if you take the Z adversarial, then we project it back, it was better, like it is better than the L2 norm. L2 norm will be smaller than the L infinity, I can guess, but yeah, we're getting in that way results.
Okay.
But we didn't put L2 results in the work.
More questions? Have you tried applying this to any real world applications as well as the benchmarks?
And no, like it's just in the, like, you know, classifier at, it's not physical, it's just digital adversarial examples.
Yes. Yeah. Okay.
So
It's interesting. Have we got time for one more question? If someone has a thought? No? Okay. Thank you very much.
thank you.
Now we have our third speaker, Mr. Xu Feng, before morning tea, speaking on quantitative explainable AI for face recognition.
I can use the arrow here. Oh, okay.
So good morning, everyone. My name is Xu Peng, and today I will introduce quantitative explainable AI for face recognition. So face recognition has gained significant popularity and importance, finding practical applications in various fields. It plays a critical role in many applications, such as custom control, online bank, smartphones, home access control, and auto transport system. Artificial intelligence, particularly deep learning, has emerged as a key technique in face recognition, offering exceptional accuracy. Many state-of-the-art deep face recognition models have already exceeded human recognition level. Based on some considerations such as security concern, recent approach in deep face recognition also prioritize model robustness and interpretability. There are some problems with the face recognition techniques. A deep face recognition model usually contains millions or billions of neurons in neural network. Black box internal structure making user difficult to interpret and understand the face recognition model decision. The lack of transparency raises concern about how decisions are made within the system. Lack of robustness indicates the face recognition system are susceptible to variations such as different light conditions and angles. This will compromise the accuracy and reliability of the technology. The low interpretability shows that it is challenging to understand why a particular decision are made, and there are some consequences of this problem. For example, the reliability concern involves some issues such as accuracy, consistency, and error rate, that can impact reliability of the model and confuse the user. To address this issue, understand the model decision is the most significant thing. One of the solution is called explainable AI. Explainable AI can enhance the interpretability of deep convolutional network, offering transparency and intuitive explanations for model operation. It can help researchers understand the system limitations and provide different kind of explanations to improve reliability and trust in critical application scenarios. There are some popular categories of explainable AI for face recognition, such as visual explanations, textual explanations, and hybrid explanations. Visual explanation-based explainable AI plays a significant role as the explanations are clear and intuitive, providing a simple way to reveal the abstract concept of the black box, such as using heat map and saliency map. In addition, many explainable AI focus on increased interpretation within the training process. However, the majority of end users use a pre-trained face recognition model and might not like to spend time to set up the hardware and software, and they want to know how it makes the prediction, not the training process. So therefore, visual explanation-based explainable AI for face recognition is more efficient and convenient to the user. One related work is called X-Scores, which is an explainable cosine metric for the face verification task. It provides a similarity map to indicate the similarity in each face section and applies an attention map to represent the contribution of each face area to the final output. User can use X-Scores as a face recognition model with some explanations. So however, there are some drawbacks of this kind of face recognition explainable AI. The potential accuracy trade-off shows that the interpretation features may compromise the accuracy of the face recognition model. Finding a balance between interpretability and performance is a challenge. The explanation generated by the explainable AI may not always be intuitive or easily comprehensible to the user. This can hinder their ability to understand the reasoning behind the model decisions. In addition, there is a risk that the explanations provided by the explainable AI may contain inaccuracy or misinterpretations, impacting the trustworthiness and reliability of the system. Based on these drawbacks, our aim can categorize into three main aspects. Firstly, we focus on enhancing accuracy by optimizing the performance loss functions and ensuring that the model decisions are reliable. In addition, some of the new visual explanation features are designed to improve the user experience. And these explanations are simplified and easily to comprehend, enhancing the interpretability of the explainable AI system. Lastly, we also ensure accurate explanations by defining the specific area, such as the background and main face area. Our method is to enhance the interpretability and accuracy of the face recognition techniques and offering more meaningful explanation to users. To achieve this, we have developed a methodology that is present in the following flowchart. The fundamental structure of the face recognition model can be generalized into three components: face input, which include data processing, and feature extractor, and face recognition model. The face recognition model generates an output that indicates whether the two input face image belong to the same person or not. In addition to the face recognition model, an explainable model is introduced and operates separately. This explainable model provides explanations to enhance the interpretability of the face recognition model. In the face recognition model, the identification loss plays a critical role in learning discriminative features. Many authors have focused on developing the identification loss to enhance the discriminative nature of the face features, such as the popular work, arc face, and cause face. To provide a quantitative explanations, the explainable model employs a regression loss which transforms the identification problem into a regression problem, and then generates a confidence score, enabling user to quantitatively analyze and understand how the model made the decision. The overall loss function consists of the regression loss and the identification loss, which utilize throughout the entire face recognition AI system. To ensure the explainable AI can offer intuitive explanations for the user to understand the face recognition model, visual explanation features are included in the model, which have some saliency map and face segment, and this explanation can assist the user to learn the model decision. One of our main objects is to improve the performance of AI's model by selecting and enhancing the overall loss function and regression loss. To identify the most suitable regression loss, we first compare some popular regression loss for face recognition. The regression loss quantifies the difference between the ground truth value and the predict value. The commonly used L1 loss measures the absolute difference between prediction and actual values. On the other hand, L2 loss is more sensitive to the outlier compared to the L1 loss. And we also explore the win-loss function that we apply for the robust facial landmark localization. However, this loss function presents challenge due to the non-continuous gradient at 0, affecting the convergence. To address this, we employ the smooth L1 loss function, which provides a stable gradient for the outlier and resolves the gradient explosion issue, thereby enhancing the model robustness. Moreover, we introduce weight values in the overall functions for each branch loss, allowing the flexibility. The weight beta corresponds to the regression branch loss, while alpha is emphasizes the identification branch loss in the face recognition model. To enhance the user understanding of the factor influencing the model decision, we introduce additional visualization features that eliminates the need for extensive analysis of unclear heat maps or saliency map. Our approach involves analyzing the most similar or dissimilar regions of the face and generate image that highlights the critical area contributing to the model decisions. For instance, given two face images, the explainable model identify and analyze the most significant region, which are the most similar region of the face in positive case, and most dissimilar region in the negative case. Our method not only identifies the most important region, but can also prioritize different face area based on their importance. For example, the explanation may highlight the eye area as the most important part, followed by the nose as the second part, and then the mouth as the third one. So we achieve this by calculating the score distribution in different face positions and determine the maximum and minimum values. The score matrix is obtained through a Hartmark product, which combines the similarity and contribution of each facial region. Overall, our visualization techniques offer a user-friendly way to comprehend the key factors driving the model decisions, improving the transparency and interpretability. To address inaccurate visual explanations in some existing models, such as S-curves, where the highlighted important region often corresponds to the background rather than the face itself, we made a definition of background and mean face area, and that reduced the inaccurate explanations. When the model shows the important area is identified in the background, we reduce the attention value assigned to that region and redistribute the reduced attention to the face area. In the given example, we can observe that initial output shows that the most important area is in the background. However, by using our approach, the explainable model successfully identifies the nose area as a significant area. This adjustment ensures that the visual explanations are more focused on the actual features of the face, improving the overall interpretability and accuracy of the model. For our experimental setup, the training dataset used is the CSRC web face dataset and trained them for 20 epoch, which is a popular dataset and same as the X-course to better comparison. Furthermore, to conduct a comprehensive performance evaluation, we test the model on various commonly used datasets, assembling both interpretability and accuracy, such as the label face in the world, celebrity in the frontal profile in the world dataset, etc. We have applied an existing explainable face recognition model called XCOS as an explainable model baseline. This model offers both quantitative and qualitative results to help the user in understanding the model decision-making process. And for the feature extractor and face recognition model backbone, we utilize a modified ResNet 50 arc face model, which can also set up in the XCOS environment for the comparison. On the left hand side, in the result, on the left hand side, the accuracy comparison across different datasets is present. It is evident that the model utilizing the modified overall loss achieve higher accuracy across all the different testing datasets. The table on the right-hand side demonstrates the average accuracy of the model significantly improved by almost 10% with the implementation of modified overall loss. The left picture shows, in the visualization result, the left picture shows the basic approach of the visualization features. It shows the original XCOS model visualization of similarity and attention map do not provide clear insight for analyzing the significant area impacting the model decisions. Our approach showing a 3x3 picture highlighting the most important area contributing to the final decision. For instance, the result in the first true positive case indicates that the eye area is the most similarity part. Without the critical area of visualization, it is challenged to determine which specific area is the most similar. This is because humans are not sensitive to subtle color difference. To better assist the user, an advanced mode is provided in the right-hand side picture, which include both similarity and dissimilarity region on the face. For the corrected explanation result, in terms of visual explanation accuracy, the original XCOS model provide an accurate and incorrect explanations by highlighting the background area as the most similar part in the true positive example. This can confuse the user as it suggests the model made the decision based on the background. However, with our improvement, the visual explanations correctly highlight the nose check area. And additionally, the table on the right-hand side demonstrates that our approach significantly corrects the explanations for more than 4% of the face image across different datasets compared to the original XCOS model. So in the conclusion, our method increased the accuracy of explainable face recognition model by optimizing the performance loss function and reduce the trade-off accuracy issues. We also enhance the interpretability of face recognition model by providing user-friendly visualization features. And although the user identifies the most significant region that affects the model decision. Lastly, we reduced inaccurate explanations and increased the reliability of the explainable model. For the limitation and further work, the current use of loss function is not perfectly address the trade-off issues, and some improvement can be made to better select the loss function to increase the accuracy. And secondly, the background and face area can be adjusted to fit different face image. For example, different face image have different face area and background region. The current attention map is made and learned by using a convolutional neural network, which poses another problem that using a black box system to learn another black box system. So some better approach can be used to establish the attention map. And lastly, some experiments should be implemented, such as if the model makes correct decision after changing the background, then the explanations is incorrect to verify whether the inaccuracy is occurred by the face recognition model or the explainable model. And here are some reference of my presentations. So thank you very much.
Questions? I'll start with one. It looks like you've generated some new explanations and compared them against the old ones. That sounds like a very difficult process to evaluate one explanation against another.
Yeah.
Did you have to do that for all of your data set? Could you automate it at all?
Yeah, it's like when you import the data set, in the training, like the training data set into the model. And after you train like 20 epoch, the output will generate both the similarity map and attention map, and also our new visualization features.
Yes, but looking at that new visualization feature, new textual explanation and comparing it with the original, that sounds like a very manual process.
It's not a manual process. We're just using the score matrix and find the maximum minimum using the hotmark product to
Okay.
To combine the similarity and attention map into one matrix,
Right.
and analyze the score matrix to find the maximum to show the most important region. Yeah.
Good. Other questions? Yep. Thanks, Dan.
Thank you for the nice talk. I have one clarification question first. What do you mean by that accuracy has been improved if you are using this proposed method?
Thank you for this question. So the accuracy is improved in two aspects. The first one is because we're choosing optimize the loss functions, so it will increase the accuracy of the face recognition model itself. And then we also using make a definition of the background and face area. So this increases the accuracy that provides the accurate explanations. So two aspects is, one is for the model itself, the accuracy of model itself provides the accurate prediction. Another one is provides the accurate explanations.
Okay, yeah. So how do you use that? Let's say that you identify some area of inputs. Then do you use that? Do you give them more weight to improve the accuracy further, or you just identify that area? That's all.
We introduced the overall function, overall loss functions by adding a weight into that, like alpha and beta, that can user can select different value for that to if they want more regression, like more accurate explanations, or they want more accurate predictions by increase the alpha value in the identification branch. And if you want more accurate explanations, you can increase the regression loss. Yeah.
Okay. Yeah, so this is a cybersecurity conference. How this work is related to the cybersecurity? So is that related to the deepfake or something like that?
Yeah, it's for the camera work, we're trying to do like using a deepfake data set to test in different face recognition model. And this can help the user to identify the reason why they make the prediction. Yeah.
Good. Thanks very much. Let's thank speaker again.
Thank you.
Now I believe we have a break until 11. Yes, morning tea time. Please be back here at 11 in 25 minutes. Thanks.
Oh，对，我先都放在这一个电脑上，是吧？
先可以。
我可能没有授权，我或者他可能没有做那个。
就直接传上就行。
或者到时候我直接用浏览器。
也可以，
可以，
也可以，对你到时候直接插到这儿，我在这儿给你开。
直接打开就行。
对，
行，那我加一下那个什么。
行行，
我加一下吧。
好，好。
今天下午我拆的那个有几个 talk？
我看一下。
哦，我下午不在这边，好像要那个拆。
哦 ，OK， 我可能真的是看一个1个小时。
1个小时。行，那你好了，这个资料。
有4个talk。
哦，是吗？我看一下是，我因为我看的时候，那个好像就没有欧玛跟那个欧玛跟
那个 Joshua，
然后现在有另外2个是吧？
对，还有
看那个拼命，
一命和成秒，嗯，
嗯
Last one. Last one is your last one.
Yeah, asking Shen Yao about the chair.
so first is
will be-
the instant response.
You cannot do that?
I can do that.
So-
Just want to know more details.
So
So not
Elena,
two talks, it's a four talks, right?
it is 4 talks.
Four talks.
Yeah, 4 talks, yeah.
Elena to Omar.
Yeah,
so
4
4.
talks. Yeah. It's true.
Huh?
It's 4, there's 4.
A four.
Yeah,
okay.
so Omar is
So-
online.
Well, Omar is online,
Yeah.
so from 1:40. Yeah.
So you are chairing, right?
Yeah. Using separation of file prevention to create solver class.
You're getting set up for your talk later. You're getting set up for your talk later.
It's done on the chair session.
In the afternoon, yeah.
Check always.
Yeah.
Yeah.
Got all your talk ready?
No, I found that I still need to add some.
I feel normal then. Yeah,
My gosh, to finish the slides.
to get it done, yeah.
Yeah, get it done, but
Yeah.
I'll probably be on the. But I'll go back and practice.
Okay.
Sorry. I'll be changing session. Oh, you'll be changing. Oh, okay.
Great.
Yep.
So errors.
Yeah, errors. Oh, I'm not sure the kicker.
Oh, yes, it's even better. Doesn't matter. The errors.
Sometimes it doesn't work.
I'm happy with errors.
Oh, okay. Yeah.
Hello, everyone. Welcome to our second session. So this session is on UQ seed funding. We have 3 speakers for this session, and each speaker, they will be talking for 15 minutes and 5 minutes for a Q&A session. So our first speaker is Associate Professor Mark Arting. So Mark's research interests include software verification, model-based testing, automated reasoning, and the correctness of smart contracts. He has worked in the software industry for several years, developing next generation genomic software and manufacturing software. He's also author of the book, Practical Model-Based Testing, a Tools Approach. So now please welcome Mark.
Thank you. I'm just going to give you a bit of an overview of what we did last year in the seed funded project about Ethereum smart contracts. How many of you have ever used or invested in a bit of cryptocurrency or used blockchain or something like that? Oh yeah, a few. Not as many as I expected. They reckon that 67% or something of Australians hold some cryptocurrency. I'm very skeptical that it's that high. Certainly a risky investment. So I'm going to give you a bit of the big picture, which I'll go over quickly. What is a blockchain? What is Ethereum? And then talk about our project where we tried a way of making sure our smart contracts correct and explain why that's important. And if I have time, I'll go on a couple of slides at the end about the future, the bigger picture. So a blockchain is like a database, but it's distributed with no trusted, one trusted server. And it's also got an immutable history. So it keeps a complete record of every transaction that's done. And there are both permissioned and permissionless blockchains. Permission basically means the servers are kind of trusted as a group, not individually. You've got to have an account to do the add transactions, and permissionless is completely anarchy. So anyone can go in and do anything. And that's what most of the cryptocurrencies are, particularly Bitcoin, Ethereum are the 2 of the most popular ones. So just to give you a visual of the cryptocurrencies, that's an area accurate pie chart of their value a few months ago. And you can see Bitcoin's #1, but Ethereum's catching up. There's a whole lot of others. And I might mention a little bit about Aptos later on. So they're important. There's lots of billions, hundreds of billions in the case, 185 billion in Ethereum, which is a lot of money people have invested into that one chain. And the interesting thing is that fair amount of that money is managed by smart contracts, which are little programs written in Ethereum bytecode, just like Java bytecode, that actually sit on the Ethereum blockchain and can execute when people send them money. And so they can sort of automate what your lawyers or your royalty agencies or your ticket sales do. So these smart contracts can automate all sorts of interesting behaviors. And they're typically written in Solidity, which is a fairly new programming language with some neat features which encourage you to make lots of bugs. And they're compiled down into EVM bytecode, which is actually stored on the blockchain. And users can interact with these smart contracts and send them money and get them to do things. The interactions are irreversible, because you can't go to appeal to a higher authority and say, oh, I made a mistake. Can you reverse that transaction? That can't be done. The code is immutable. Once you put a smart contract onto this blockchain, you can never change it again. The bugs are frozen there forever, and it's public, so everyone can see your bugs and take advantage of them. So this makes it a little bit important to get the contracts right. Of course, you test them, but testing can never find all the bugs. So our project is saying, can we use a theorem prover to guarantee there are no bugs of a certain kind, or that the functionality, a certain invariant is always maintained, something like that. And there's over 1 million contracts on the Ethereum blockchain, managing over $100 billion. So it's fairly important to get them right. Here's an example toy casino contract. The smart contracts are on the left. So there's one operational method, if you like, to create a game, and you pass in a secret key, which is going to determine, this is a game where players can put some money on and say they're going to bet its heads or tails. And if they're right, they get double their money back. Actually, it's supposed to be 1.8 times the money back. And if they're wrong, they lose their money. So it's just a simple gambling game, kind of like 2-Up. The casino operator starts the game with calling create game, giving a secret key, which will later on determine whether it's heads or tails. And then the player calls the place bet, saying, I'm going to bet 1 ether, which is probably a lot of money to bet, that it's heads. And if they're right, a little bit, well, that gets recorded, and a little bit later, the casino operator can do the decide bet and pass in the expected answer, and then a 1 or a 0, and then either the player wins or the operator wins. If the player wins, they get paid out 1.8 ether. If they don't win, then they lose it, and it goes to the casino, because gradually the casino will build up money. So there's the Solidity code for one of those operations, the decide bet function. And it's, if you're interested in cryptography, it's just interesting to see there that, I'm not sure if I can actually point to that. Oh, there, I found it. This, the public number that comes in here is encoded, and that has to equal the secret number, which was placed at the beginning of the game to ensure that the casino operator can't cheat. And then depending on whether that's even or odd, the answer is actually heads or tails. So it's safe from both sides, and it'll either do the call the player wins helper function or the operator wins helper function, and then go back into the starting state again. So fairly simple code, but when you compile that down to bytecode, it becomes a bit larger. And this is actually, we don't trust the compiler, so this is what we actually want to verify. And I noticed that, so that's, I don't know, 50 or so instructions, and I haven't even filled out the operator wins and player wins there. There's another 29 bytecodes inside those. So it's quite a largish bit of code when you look at it on the actual bytecodes. We want to verify this. So the question is, can we set up a verification system for this, and can we make it automated? To do that, we decided to use a Microsoft tool called Veil, which is a language designed for modeling assembly language and automated proving using a Z3, the Z3 solver. And so to do that, we'll model the semantics of the EVM bytecodes, and then we'll build our smart contract on that. Veil will translate it to a language called F*, which is kind of a functional language, a bit like F#, but with automated support for a theorem prover built in. And from that F*, we can also generate the actual EVM bytecode. So Veil is a tool for verifying assembly language. It's been used for verifying really high performance cryptography code where you unroll loops and do all sorts of fancy optimizations and you want the assembly to run as fast as possible. It's basically aimed at x86 and ARM code, but we modeled the Ethereum bytecode in our project, so we could actually reason about Ethereum bytecode. And the idea is that these little purple blobs at the bottom might be each individual instruction, and Veil gives you sort of a higher level view of that instruction, and you combine instructions into higher level methods again and gradually build up your level of abstraction. So you're not reasoning about the bytecodes individually, you can build it up to a higher level. So we define a whole lot of files, and then we write a contract, compile it, get the F#, and it gets verified. And if you're lucky, it comes back and says, yes, it's all the properties you want are true. This contract is safe. So there's a whole lot of different levels we had to build, some EVM microcode, and the denotational semantics of the EVM interpreter, including the memory regions and things like that. And then on top of that, we build up all our Veil procedures until we get to the very top level. So here's our first lot of results, is we managed to verify initially some really small case studies, like just a simple counter example. And then we verified the casino case study, which was quite a bit larger. It's I only showed you a tiny bit of it. There's about 24 procedures, 1,200 lines of specification, 222 lines of code. Do you notice anything interesting about those two numbers? How many more lines of specification are there than code? 6 lines of specification for every line of code. That's a lot. It's a lot of verboseness to explain the behavior in a way that a computer can understand it, more than the code itself. I was kind of expecting a 1-to-1 ratio. I was a bit surprised that it took us 6 times more lines to describe the expected behavior of the casino. But apparently that's not too abnormal in these kinds of projects where you want full functional behavior verified. And we also did a coin example, like an ERC20 token, if you know your Ethereum. That was a little smaller, and some helper procedures as well. And so we successfully verified all those, and the theorem prover came out in every procedure and said, yes, they're all correct. But the truth is that sometimes just by changing one line or reordering sometimes, the whole proof system could just go incredibly slow and take hours and hours and never finish. And also the specifications, these 1,200 lines, were a lot bigger than we really wanted them to be, and bigger than I think a real user would be happy with. Wasn't very good from that point of view. And we found out that Veil is just not very flexible in terms of its type system and language and things like that. So if I was doing this project again, I wouldn't have started with Veil. I would have chosen some other tool. Z3 is great, but the front end to it, Veil, wasn't great. Just mention one thing though, which shows you some of the advantages of what we did. So on the left there in black is our specification of the add bytecode in Ethereum. And you can see it's got some preconditions, which says basically the stack can't be full, and the top of the stack plus the next thing in the stack down has to be less than the maximum integer, which is 2 to the power 256. It's a very large number. So that's making sure there's no arithmetic overflow after you add those two numbers together. And if you do that, then the rest of it describes what happens. Something gets pushed, the sum gets pushed onto the stack. And this is actually implemented by the add instruction. Now that's a nice specification. It assumes that you're not allowing overflow. The nice thing is we can refine or correctly implement that specification by 2 versions of the real code. One, I'll just zoom it up a bit, the add wrap, which does, see the little percentage there? It does modular arithmetic, like the real hardware does. And the other one, I'll zoom up the other one, has an if then else to check to see if there was overflow, and if it does, it raises an exception essentially. And both of those implementations, one of which is what Ethereum 7 version 7 does, and one of which Solidity version 7, and one of which Ethereum Solidity version 8, both of those are correct implementations of our original spec or original implementation. So as long as we use the left-hand side all the time in our proofs, it doesn't matter which of the right-hand side we use at runtime. So that's a really nice way of keeping the proofs simple, but allowing a complicated implementation. So conclusions, yep, you can use Veil, but I wouldn't recommend it. If there was a lot of changes to Veil, it could perhaps become more useful, but as it is, it was a bit of a pain, and next time we'll be looking for alternative options. So is Ethereum the answer to everything? I just wanted to finish with a couple of slides on what perhaps we should be doing. How should we be writing contracts? Because Solidity is very, very error prone and doesn't have a formal semantics, although some people have worked on it. There's other languages that might be better, like DAML is a sort of a functional language with a higher level notion of agreements and signatories and privacy and rights and all these kind of things built into the language. Perhaps that's a better option, although the ASX just lost $250 million trying to use DAML for their process. Or perhaps Move, a language that came from Facebook, inspired by Rust. That is a language that already has this idea of verification built into it. And it's used for the Altos or Aptos chain and a few other chains as well, which are becoming quite popular. So there are options there which actually have this verification built in. So that's an idea for the future, is to look for better languages as well as better tools. Thank you.
Thank you. Thank you for the presentation. It's very interesting. Could you comment on the transition from the current encryption schemes based on prime factorization to something that's post-quantum, like these lattice-based encryption schemes, and how you can implement that using blockchain?
No, not at all. No, sorry, it's outside my area of speciality, but I know people are working on it. And yeah, probably other people here have got more of an idea than that. But sorry, quantum is out of my league at the moment.
Thank you.
Probably this is probably a very ignorant question because it's outside of my field, but the deal with verifiability, is the tool you're using to do the verification itself verified? I assume it doesn't verify itself.
Good question.
So are we just moving is it easier to convince a human being that the verifying tool is itself accurate? And so then we can be confident that the things that it verifies is accurate. Like, are we just not saying, okay, instead of trusting this, we're now trusting this?
Yep.
How is it? Yeah, what I'm getting at.
Very good question. It gets to the heart of the matter. What is our trust basis? In this case, yes, you're right. We're putting probably not Veil itself, because that just translates into this F-star language, but the F-star language plus the Z3 prover, we're putting our trust in them. Now, they have been used for a decade or so by lots of projects, and bugs have been found, so they're not foolproof. Because it's kind of an independent thing to do, you can bet the same error is not going to happen there as happened in your code. You're kind of getting an independence result, but I wouldn't trust them with my life, probably. But there are other provers. Another one I use in another project, Isabel, which has been around for 40 years, is based on 11 axioms, which mathematicians have studied thoroughly. That one there, maybe I would trust that one with my life. It depends. There's levels of trust in provers as well. One more question.
So I may sound dumb, but it's not my area. So when you say you're doing verification, is it verification per transaction? And because Ethereum, as far as I know, it uses gas as a fee for per transaction. So does your whale support that kind of mechanism of gas? And so yeah, are you testing for each transaction? Are you verification having for each transaction? So there is a each gas fee involved.
Great question. So we can take into account gas. That's handy because it means automatically that all loops terminate and things like that. If you run out of gas, the transaction rolls back. I think in this model, we ignored gas, but there are other models of the EVM that do include gas. And the other question you asked is, are we verifying each transaction? No, we're verifying all transactions. So sort of at compile time, like a type checker, we guarantee that these errors can never happen, regardless of what the input is or how many times it's called. So that's the attraction of verification compared to testing or just verifying one transaction. Thanks.
I have a quick question. So since I also work in the same area. So the question is that I have seen you have an example. So in that examples, you have shown that if there is a buffer overflow, so we can formally verify that yes, the code. So it's there is a possibility of buffer overflow if we are not checking the boundary. So did you also check the race conditions as well? If there is a function, that function could be used by multiple contracts. So which means that there is a variable, and the value of that variable can be increased by one function. And when the other function is using that variables, it's actually getting the updated values, not the previous one. Or the function when it is using, it is getting the previous value, not the updated one. So can it also be checked using this formal verification method using Veil?
We took a sequential execution model, which I think is what actually happens on Ethereum. Only one contract can execute one procedure at a time, but that can update a variable and then later on another one can come on. But yeah, we took a sequential model, not a concurrent model.
Okay, thank you. Thank you very much. Please join me. Thank you, Mark, again. So our next presenter is David Hunt. Dr. David is a lecturer in cybercriminology, and since 2009 has been working collaboratively with the Australian Federal Police on a series of research projects associated with the triaging of online child abuse material reports. David's research interests has been law enforcement training regimes, information warfare, countering online child exploitation, and the nexus of intelligence and law enforcement in the area. So it's a long line. I'm not going to but join me, please welcome Dr. David Hunt.
Ladies and gentlemen, good morning. Thank you to the conference organisers for the opportunity to talk this morning about a UQ cyber research funding project that concluded in about September of last year. I am obliged just to give you a trigger warning based on I'm certainly not going to go into any detail associated with child sexual exploitation material, but it is a heinous crime, and it can be triggering for some people. So if you feel the need or desire to leave the room, I certainly won't be offended by that. I'd also like to acknowledge the co-collaborators on this particular project. Three from the University of Queensland, Renee, Richard and Ruby, but also Warren Bulmer from the Australian Federal Police, who was the project coordinator. Sorry, which button? My apologies. Oh, that one. Okay, there we go. Just to give you a little bit of background in relation to this project, child sexual abuse material, or CSAM as it is known, is a threat environment from a cyber criminological point of view that continues to grow in both complexity with offending rates on an upward trajectory. And that has presented a range of associated challenges for law enforcement in how they deal with these crimes. So just to give you an indication, the National Center for Missing and Exploited Children, which is a US-based federally funded organisation that is effectively a clearinghouse for the reporting of child sexual abuse material, received 21.7 million CSAM alerts in 2021. And that was approximately a 21-fold increase from 2014. And when I'm talking about CSAM alerts, I'm talking about both child sexual exploitation videos, but also still photographs. To put that in context from an Australian point of view, the Australian Centre to Counter Child Exploitation, which is based here in Brisbane, handled 36,000 reports in 2021, which was an increase from just over 5,500 in 2014. This type of criminological threat is what they term a AAA threat, because accessibility is increasing, anonymity of offenders is increasing, and the adaptability of offenders is changing, and they are becoming more agile in their offending pathways to avoid detection and to put hurdles in front of investigators. This particular cyber seed research project was on the back of several other projects that had really commenced in 2019. Based on this escalation of offending, the Australian Federal Police came to the realisation that they were not positioned with the risk assessment tool and the processes required to handle the increased number of reports that they were having to deal with on a daily basis. So we at UQ were engaged as a research team to go in and review the way that they were conducting triage, the tool that they were using, and then to redesign and implement a replacement decision support tool for them to facilitate their processing of these child sexual abuse material alerts. So we did that over a period of 3 years. So just to explain to you the process that is applied by law enforcement, and particularly the Australian Centre to Counter Child Exploitation, just to provide you a little bit of context. So the primary feed that the ACE, as it is termed, receives is, as I said, from the US National Center for Missing and Exploited Children. And the ACE receives the cyber tip alerts and a package of data from NCMEC in the US. And the reports that the ACE receives are geolocated to Australian offenders, or it's believed that the geolocational data is associated with potentially Australian offenders. And there are supplementary feeds that also come in from other agencies and other avenues. So these CSAM cyber tip alerts come into the Australian Centre to Counter Child Exploitation, located in Fortitude Valley here in Brisbane. In that centre, they apply the tool that we developed over 3 years, which is termed the Triage Referral Investigation Support Tool, or TRIST. And what that tool does is that it provides an assessment of the content severity, an assessment of the victim impact and offender identification, It assists the investigators to make a determination as to possible investigative action that can be taken in relation to the suspected offender, and it will assist them to allocate resources to investigate the matter further. And out of that process, some decisions and actions are then taken by law enforcement. So the matter is either referred for further investigation outside of Australia, for investigation within Australia, or if there is not enough data to further the investigation, that information is retained for possible collaboration with other data that comes in subsequently. So it's never thrown out, but it's stored for matching purposes down the track. The significance of this particular project, the follow-on cyber seed funding project, relates to the red arrow. So after we finished the final project in the development series for TRIST, the AFP, as happens, introduced some new systems. And so we were interested to know whether the introduction of those new IT systems and information management systems had an impact on decision-making by the triage staff as they went through this process. So if they had access to more fulsome information relating to offenders, potential offenders, geolocational data, etc., would that impact on their decision-making as they went through the triage process? So there were two broad aims associated with this project. What does having access to more fulsome information in those cyber tip alerts actually, what impact does it have on the triaging, the prioritization and the referral process? And if there is an impact, does the AFP need to go back and adjust the tool and the internal algorithms, etc., that we had developed for them in concert with those impacts? So we use what is termed in the social sciences a phenomenographic approach, which is basically giving an interviewee an opportunity to tell their story. So we sat down with the 8 members of the Child Protection Triage Unit, and they form the basis of the team that does this work at the ACE. And we asked them questions about how they actually go about triaging these reports when they come in. What processes do they use? What helps or hinders them? How did they actually learn to carry out the triage process, and what impacts on their decision-making? What role does technology play versus, for example, their professional experience as law enforcement officers? So I guess in a nutshell, probably the key outcomes or the results that we found was that the tool that we developed over a process of 3 years, the federal police were very happy with the effectiveness and the efficiency of that tool. It is certainly helping them. It is facilitating the speed of data entry for them. It's assisting them to keep up with that tsunami of increased reporting that they're experiencing. And it's also allowing them to focus on the most heinous and high priority cases for further investigation. It does assist with their decision-making. There were some minor concerns about some of the particular ratings contained within the tool being too rigid or too ill-defined. And we have subsequently gone back and worked with the AFP to adjust the wording of some of those questions. I guess that last point there, that while TRIST supports decision-making, from these interviewees' point of view, and it's a perception and an opinion that has been largely validated across the law enforcement community in this particular crime space, technology can assist, but it will never remove the role played by professional decision making. And so there are then a series of follow-on questions associated with, well, how do you measure, how do you actually capture that professional knowledge, and how do you convey it to more junior analysts and law enforcement officers? So the interviewees had a number of recommendations, and they weren't major. I guess they were generally happy with the feasibility and workability of the tool, but they suggested that some of the weightings might be adjusted based on access to more fulsome information. And one of the other key findings was that even in a team of 8 professionals and their experience of working in the triage space went from they'd only been a member of the team for about 8 months through to other officers who had been part of the team for about 5 years and were dealing with this stuff on a daily basis. So that was the range of experience. There were different understandings of the triage process within the team. So we found that very interesting from a social science and a criminological point of view. If you've got individuals that are working in a team trying to handle complex decision-making tasks, how do you harness the experience of the more experienced and the professional judgment of the more experienced, and bring the more junior team members along on that journey. And one of the key outcomes of this process was the fact that we affirmed that professional judgment really does continue to play a key role in triage and referral when it comes to child exploitation material, child sexual abuse material. So overall, we identified a range of operational and procedural impacts associated with the introduction of that new information management system. But we also confirmed that the tool that we developed over 3 years, which was in some ways was pretty groundbreaking in this particular crime type, it was working for the AFP. It's improved their efficiency and their effectiveness in dealing with this. And whilst there are some considerations to be taken on board with new technology, you can never throw out the role of professional judgment in decision making, even when you have access to more fulsome information. So the outcome of this project was that we are continuing to work with the, it's sort of moved out of the cyber tech realm now, but we're continuing to work with the AFP as to where we can possibly take this research further when it comes to professional judgment in law enforcement decision making. So, thank you. Sorry, not very techy.
I have a question, David. So in most of the cases, cyber attacks are happened by the cross-border raiders, so who are from all around the world. So it could be from any countries.
Yeah.
So what sorts of mechanisms we should use? So if we are tracking, or if we want to prevent, or if we want to protect ourselves from these types of attackers?
So I guess there's a there's a saying in the intelligence realm that forewarned is forearmed, and law enforcement increasingly are dedicating a lot of time, a lot of effort, and a lot of money to prevention and engagement strategies. And they are linking in with organisations such as the Office of the E-Safety Commissioner to make people more aware of the dangers that exist in terms of child sexual exploitation. And it goes beyond it. A lot of the threat is increasingly becoming monetized as well. So there is the whole separate issue of online child exploitation becoming a business model for some cyber criminals. So there are, I guess there are a host of prevention and engagement strategies that are that law enforcement agencies are working with government and working with service providers as well, and the public to develop information campaigns so that awareness across the board is increased. So awareness is probably the first line of defense.
Yeah, thank you very much. Please join me thanking the once again. Okay, so this is the last talk for this session. And our presenter is Associate Professor Gianluca Di Martini, if I could pronounce it properly. So just a brief introduction. Dr. Gianluca is an Associate Professor in Data Science at the University of Queensland, School of Engineering, Electrical Engineering and Computer Science. His main research interests are information retrieval, semantic web, and human computation. His research has been supported by the Australian Research Council, the UK Engineering and Physical Sciences Research Council, the EU H2020 Framework Program, Meta, Google, and Wikipedia. He has published more than 200 peer-reviewed scientific publications, including papers at major journals, and received several best awards. He's a senior member of the ACM and ACM Distinguished Speaker, and has been a TEDx speaker in 2019. So please welcome Associate Professor Gianluca.
Thanks. Good morning, everyone. So I am a computer scientist based at the School of Electrical Engineering and Computer Science, as it's called now. And I'll tell you about this project we built, this system we built last year during the federal election campaign. This was an interdisciplinary effort with colleagues at the School of Political Sciences here at UQ, and it involved around 10 people, including undergraduate students, PhD students, postdocs, lecturers, and so on. So let me tell you where this is coming from. The research my group has been doing in the last few years has been looking at the issue of misinformation online. We have done different things in this area. On the one end, we looked at how we can support people spotting misinformation by themselves. We studied how humans perceive, how people perceive misinformation, how they interact with it, and really what we can tell them in order for them to make up their mind of what they should trust and what they should not trust online. We also have built explainable AI models to automatically detect misinformation. And they not only detect misinformation, but they generate a natural language explanation, a piece of text telling you why something is fake news. But I strongly believe people would not trust an AI telling them this is fake news, trust the system, because they even don't trust the journalist. So I really see the way forward is transparency and increasing and telling people more about what's going on. What are the conflict of interest? What are the financial interest of people making a statement? And then people can make up their mind on what they should trust and what not. So this is in a way the foundations of this CyberSeed project that led us to build a dashboard that we put publicly facing on the UQ domain during April and May 2022. This dashboard was tracking political advertisement on Facebook live during the campaign. And we were showing a number of things that I will tell you about today. So, for example, we were looking at the spend, so how much money different political parties have invested, have paid to Facebook to show to Facebook users sponsor posts. So what you can do is basically you can publish, start an advertisement campaign, and then you decide this post should be seen by a specific segment of the user base. And you have micro-targeting functionality saying, I want this post to be seen by people who own an iPhone and go running on the weekend and go to the movies once a month. So the data we had allowed us to do a number of data analysis. So, for example, just looking at the spend over time. Let's see if I can put, yes. So we can look at the spend over time. This is the volume of money spent on the platform. That's the election date. This is when the election was announced. And you see there was a build up before the election was announced from the different parties and so on. So to go a bit in detail, just to explain you what data was available from Facebook and also what data we extracted and additionally created from what was available. So what we did is every 6 hours during the election campaign, we fetched all the ads which were running live on Facebook, all the political ads running live on Facebook. For each advertisement, if you are a Facebook user, this basically means you get a Facebook page that is posting paying for the ad, a piece of text, and in the vast majority of cases, you get an image or a video after the piece of text. We knew which Facebook page was paying for it, how much money they were paying for it, and also we had some targeting information. So who was seeing, who was shown this ad, and we had targeting information only at the level of gender, age, and state in Australia. But of course, advertiser can target much more fine-grained than this, but we just didn't know that. And this was the data we got. In addition to that, we did apply machine learning models on the data, both on the images and the text, to do things like topic modeling, sentiment analysis, misinformation classification, and also geographical classification at the electorate level, which was not available in the original data. We use human-generated labels to train supervised machine learning models, and then we apply the models on the entire data set. And we are very thankful we had the political scientists to do the difficult annotations, for example, matching candidates to electorates and having and Facebook pages to parties and so on. Okay, so just for those interested in the back end of all this, we run it on Amazon AWS, but we did all the machine learning at UQ. So the pre-processing, well, the live processing of the data was done at UQ, but then the dashboard was stored on, was running on AWS. So we were storing the data on S3, and then we had a pipeline that in the end was serving the dashboard across 3 different production systems, one on Power BI, one as Tableau, and one as RStudio. And this was because we had different users in a way using the data differently. Okay, so what happened during April, May last year? First, unexpectedly, a lot of media coverage. We got a lot of journalists interested in this. From ABC, you might remember during the pandemic, the guy with the big screen with the COVID data. That guy was very interested in our data, but generally a lot of media outlets. So we got most of the visit and we launched really the dashboard the moment the election campaign, the election was called. So we were waiting for it like everyone, and then we let it run until election date. Most of the people obviously visited from Australia, but there was quite a lot of journalists from US interested in the election. Over time, we had quite regular visits. There was some spikes when we released it, and UQ had some media releases. And then when we got some national news coverage, we also had increasing visits to the dashboard. So what I found very interesting and surprising for me is that I expected this. I wanted to build this for the people voting in the election to know what's happening and how they are being advertised to. But in reality, who was really most interested in all this was journalists. We got a lot of people, a lot of journalists contacting us, asking my colleagues in political science to go and sit on the TV shows to talk about this more than the actual voters going to the polls. Okay, and as a data scientist, what I loved of this is that after the election day, we have all the data there. So we can start to, without having the rush of the live data monitoring, start to look at what happened as a post-hoc analysis. So you can start to ask questions and look at the different patterns. Obviously, the natural question everyone wanted to see is how much money is being spent and whether that correlates with the votes. So on the left, you have the votes. On the right, you have the spent. And here you have a comparison. So you see that more or less, it's a correlation, obviously, not a causation. But you see a correlation between how much money are being spent relatively to all the others versus how many votes the party gets, with some exceptions. Some parties will spend a lot of money, which are not necessarily, there is not a big return on investment there. Another very interesting exception is the opposite. A party that didn't spend much on Facebook, they had a different communication strategy, but they ended up getting more return on their spend. So I'll just tell you a couple more interesting observations given the time available. As I mentioned, we did the topic modeling. So we extracted the main topics that these advertisements were talking about, and then we look at who is talking about what. So you see here an example. Here you have a party, and then here you have a topic, and then the colors represent which party is talking about that. Let's take an easy one. The topic freedom is talked a lot about this yellow party. Climate is talked a lot about nationals and so on. So what's interesting, what I found very interesting, especially early in the campaign, you don't see here a temporal pattern, but early in the campaign, there was a lot of cross-party advertisements. So Labour talking about liberal and liberal talking about Labour, but then later on there was a lot of we are good close to the election date, but at the beginning it was a lot of they are very bad, so vote for us. And then you have different approaches, right? You see that the Greens were instead talking about actual topics, not about how bad the others are, including climate, Medicare, which was very, in a way, consistent with their program and promises. Right. Then I mentioned we had some targeting information. So who are these ads shown to in terms of age and gender? So here you see that on the left you have female, on the right you have male, and you see that there is a targeting, especially around the 25-34 age range, and this in a way matches well the demographic of the Facebook user base today or last year. But then if you compare parties, you see that there are differences. For example, the Greens on Facebook, they targeted more female than male, while on average you have more targeting of male than female. But again, keep in mind that this is Facebook advertisements only, while obviously an election campaign has multiple channels, and the Greens were knocking doors more than spending money on Facebook, and this is reflected in this money spent versus vote correlation we have seen before. Okay, last thing I'll mention is a student who just finished and graduated last week, who has used this data a posteriori after the election campaign to build machine learning models to automatically detect propaganda in this data set. So the ads on Facebook during the election campaign. Here you see the red amount is how much propaganda has been detected over the election campaign. And here you see an example of one ad which has been labeled as propagandistic. Scott Morrison cat and neglect are hurting school name, vote for kids, not cats. And what was beautiful is that this ad was targeting different subset of the user base by just changing the name of the school. So you can micro-target is the children of this person going to that school, then you show this ad. And you show a different ad to different people. That's a good example of micro-targeting. Okay, so for the sake of time, I'll stop here, and thanks very much.
Great presentation. So I was wondering, did you guys work out because you could see which parties targeted specific ages and demographics, did it work in terms of their voting? Could you see that, or?
So for certain parties work better than others. And again, I think a big winner of last election campaign were the Greens that didn't use Facebook as a mean to gain seats in parliament. I think again, this was just a very small subset of what an election campaign means. Was interesting to compare, I think, the two big parties' strategies. Again, there is a lot of data we can still look at, but yeah, generally, I think at least the two big parties had a very expected pattern of advertising, targeting the most represented users on the platform, a bit across the spectrum, while the smaller parties were more, in a way, trying different techniques and focusing on certain age range or population type.
The follow-on question from that, I guess it's hard to track causality because you've only got one election, but if you ran this for the next few elections, you might start seeing some patterns and causal changes and things. Are you running it for the vote that's happening now? Because that would also be interesting. There's a lot of misinformation and propaganda around about that. It would be fascinating.
So let me give you two answers. Yes, it would be nice to do it longitudinally, but I would imagine that strategies would change, right? Every election is different. The strategies used may be different. So yes, we could find patterns, but maybe the patterns are changing also over time. So for the current campaign, we are doing the data collection, but we are not doing the live tracking with the dashboard like in this one, but we have the data there, so we can do exactly this analysis.
That's even better because your dashboard doesn't bias the results.
The results, yeah, exactly.
Thank you for the presentation. It was really insightful. I'm just curious, what was the reason for choosing Facebook as the platform compared to like Google Ads or any other platform? As you mentioned, it was a very small subset of an election.
I mean, the data was big, but there are other channels that obviously are used. Facebook data was available. Google Ads data would have been available. But it would have been impossible to have all coverage of all possible strategies, especially Greens knocking at doors. It's very hard to track unless you are the party. So as an external observer, we picked Facebook as the one providing the richest data. And again, the only other options were Google Ads. And yeah, that's it.
I feel like it would be interesting to see the correlation between Google Ads because you can see what kind of websites those individuals go to and already track their political leaning compared to Facebook, which has, you know, demographics data, potentially like, you know, gender, any other traits, whereas Google offers more comprehensive detail based on user browsing.
Yeah, I'm not sure I would agree with that. The targeting options are different. I think Google is based on browsing. Facebook, on the other hand, has very rich profiles of their users by tracking all they do on Facebook, but also beyond Facebook through cookies. So it would be hard for me to pick which is better at micro-targeting. They're doing a very good job. That's their main business model for both of them. But yeah, it would have been nice to compare the two.
Thank you.
Hi, really interesting presentation. Did you look at potentially other explanatory variables like the virality of videos or images and kind of the organic reach compared to the paid reach on top of that?
Yeah, very good point. We did not do that. It's very difficult to have access to organic content. So the sponsor content is in a way disclosed by these platforms for a number of reasons, but the organic content, it's very hard to obtain. So we didn't, but it would be very complementary to the sponsor content.
Still have some time because one will be solved at 12:15, right? So yeah, if anyone has any other questions. If there is no question, there is one. That's good.
Yeah, thanks for the presentation. I'm just curious about what kind of privacy controls you had in place when it came to measuring all this data involving age and demographic.
Privacy of the end users.
Yeah, that's right.
Sure. So we really know nothing about end users. What we know is for each advertisement campaign, so a sponsored post, the distribution. So imagine you have one post which someone has paid to be displayed, and this will be displayed 10,000 times. We know that out of these 10,000 times, it has been shown 300 to someone who on Facebook is female and between 20 and 34 years old in Queensland. and then 200 times to another segment and 100 times to another segment. That's all we know. We know nothing more about them. Obviously, Facebook does know exactly who has seen what, but we do not.
Okay, thank you.
One more questions from audience.
Just following up on that, you said you track things down to the electorate level in some case. So that implies using the IP address, or how are you getting a bit more detailed?
So the other way around, given a post made by a Facebook page, the Facebook page was in a way aligned to a party, to a political party. And then based on the content of the post, we classify it as targeting a specific electorate. The easiest example is there is a candidate name mentioned in the ad, and we know that that candidate is running in that electorate. So we could do this matching for all ads, and then we can do statistics. So in the last election, Kuyong, where we had one minister running with an independent, and the independent won, there was a lot of ads in that electorate, but we didn't have this information. We extracted it by analyzing the content of the ads, but not looking at who has been shown the ad, because we don't know.
Thanks.
Any other questions from audience? One more. No worries, we have the luxury for spending time.
Thank you. This is quite interesting. I was wondering, like, this whole process, I mean, you have used like different technical stuff as well as like people skills to do certain things, right? How easy, or like what are the challenges if this was to like package like an off-the-shelf solution or something, just some software you could install and people could run like campaign evaluations? Is it possible at this stage, or is there like too much still human involvement in this process?
Yeah, very good question. I wouldn't say it would be possible like one-click deploy for the next election. There would still need to be some customization to be made. So we had interest from Germany to run this. And obviously in Germany, the electorates are different. We had a database of candidates that would be different. But if you could do all these changes and adaptation, then it's possible. So to train our machine learning models, we collected human labels from crowdsourcing platforms. Those human labels we might need to collect again to retrain a model that works better for the next election. So it's not one click run again, but it would require doing the same model training and pre-processing for a new election or a new place.
Do you expect like between geographies to be like considerable domain shifts? Like is a model trained like maybe in Australia usable still in Europe?
That's a good question, which I would love my colleague in political science to answer. I learned a lot of things about differences. One thing is voter suppression. There is a lot of voter suppression in US in this type of data, in this type of ads, but not in Australia because it's mandatory. So in US, you really win by not having certain people go to vote for your opponent. And there are a lot of ads convincing people not to go to vote. And it doesn't happen here. So there are apparently some unique things in the content that might require a bit of adjustment in what we decide to classify and extract from the data. But my expertise is not enough to, in a way, give you all the differences across different elections and places.
Okay, one last question. So first, I would like to thank you because it was very comprehensive analysis, lots of results you have presented. I have seen a slide which shows that the percentage of votes for each party and also the amount they spent. But that's not the true representation, because how many people are using Facebook? How many people you are reaching that? So it doesn't represent the original figure. So how actually you justify that?
Yeah, as I said, it's a correlation. It's just two numbers, one next to each other. This is not the total amount of money spent by a party in the election campaign, but only on Facebook. And for example, certain parties spend a lot of money on TikTok. Some parties spend a lot of money just going on the field and meeting people and running events physically in spaces. So it would be nice to have one next column in this table showing the total spend that the party would have. But that would probably be easier to guess based on the size of the parties and the budget they have to run these campaigns.
Yeah. Have you considered people's interaction or impression on those public ads as well?
So we didn't have data about reactions and comments on these ads. We did have data about impressions, so how many people have been shown a specific ad, but that didn't bring much information. It only tells us in a way which are the segments which are more expensive to target. It is well known that young females are very expensive to target because there is a lot of organization targeting them, trying to sell products. So if you want to do political advertisement, it's very expensive because there is a competition for that segment. This is what the impression data would have given us. But again, we didn't have reactions or comments.
Thank you. Thank you very much.